In 1935, Albert Einstein and Nathan Rosen published a paper that accidentally created one of the most dangerous ideas in modern physics. They showed that the equations of general relativity allow a bridge connecting two distant points of spacetime. For nearly 90 years, that bridge has captured the imagination of physicists, filmmakers, and dreamers who believed it could become a shortcut through the cosmos. But here is the truth nobody wants to hear. Every single attempt to make that bridge real, to open it, stabilize it, send anything through it, has revealed the same devastating conclusion. The universe allows wormholes to exist in mathematics. It forbids them from ever working. What scientists actually found is far stranger and far more important than any portal. If you enjoy journeys that challenge everything you thought you knew about reality, hit that like button and subscribe. Your support helps us explore the deepest questions in science together. Now, settle in, get yourself comfortable, let's begin. In 1915, a physicist who had already rewritten the laws of motion published a set of equations that would reshape humanity's understanding of the cosmos. Albert Einstein's field equations of general relativity did something no previous theory had accomplished. They described gravity not as an invisible force reaching across space, but as the shape of space itself. Mass bends the fabric of space-time. Objects moving through that curved fabric follow the straightest paths available to them, and those paths look, from our limited perspective, like gravitational attraction. A planet does not orbit a star because an invisible rope pulls it inward. It orbits because the star has warped the geometry of the surrounding spacetime into a curved basin, and the planet rolls along the contour. The equations were beautiful, compact, and ferociously difficult to solve. Einstein himself could only find approximate solutions for most physical situations. But within months of publication, something extraordinary happened. A German physicist named Karl Schwarzschild, serving on the Eastern Front of World War I, working between artillery calculations in the trenches, Schwarzschild described the precise geometry of spacetime surrounding a perfectly spherical, non-rotating mass. He mailed the result to Einstein, who presented it to the Prussian Academy of Sciences in January of 1916. Schwarzschild died 4 months later from an illness that developed while he served at the front. He never learned what his solution would reveal. The Schwarzschild solution predicts a boundary surrounding any sufficiently compressed mass, a surface where space-time curves so steeply that nothing, not light, not radiation, not information of any kind, can climb back out. Cross this boundary and you are committed. Every direction you can travel, every path available to you through space-time, leads inward. We now call this boundary the event horizon, and the object it encloses a black hole. The term would not be coined for another 5 decades, but the mathematics was already there, buried in Schwarzschild's wartime calculations. But the Schwarzschild solution contained something else. Something far stranger than a region from which light cannot escape. When physicists extended the equations beyond the event horizon, pushing the mathematics past the singular point at the center where density becomes infinite and curvature diverges, they found that the solution did not simply end, it connected to something. The interior geometry of the black hole opened into a second exterior region, a mirror image of the space-time outside, as if the universe folded through itself and emerged on the other side. For 20 years, this feature sat in the equations largely unexamined. Then, in 1935, Einstein teamed with his colleague Nathan Rosen to study it explicitly. Their paper described what they called a bridge, a geometric connection linking two asymptotically flat regions of spacetime through a narrow throat. Einstein and Rosen were not trying to build a cosmic highway. They were trying to model elementary particles using pure geometry, hoping to eliminate singularities from physics by replacing point particles with smooth bridges. The idea was mathematical, abstract, and had absolutely nothing to do with travelling from one place to another. This bridge became known as the Einstein-Rosen bridge, and for decades it remained an obscure mathematical curiosity, discussed in technical journals and ignored by virtually everyone else. Then John Archibald Wheeler changed everything. Not by changing the physics, but by changing the name. In the late 1950s, Wheeler coined the term wormhole. The metaphor was vivid. Imagine a worm eating through an apple. Instead of crawling across the surface from one side to the other, the worm burrows a shortcut through the interior. The name implied a tunnel, a passage, a secret corridor connecting distant locations through the hidden interior of space-time. The metaphor is spectacular. It is also almost entirely wrong. The Einstein-Rosen bridge is not a tunnel you can walk through. It is not a corridor connecting two doors. It is a geometric feature of a mathematical solution, a topological connection that exists in the equations, but behaves nothing like the passageway the word wormhole suggests. Understanding why requires looking carefully at how physicists actually map the geometry of space-time inside and around a black hole. The original Schwarzschild coordinates create a deeply misleading picture. In these coordinates, something apparently catastrophic happens at the event horizon. The mathematical expressions blow up, producing infinities that seem to indicate a physical boundary where space-time tears. For decades, physicists argued about whether this meant the event horizon was a real barrier, a place where the laws of physics broke down. The resolution came through a technique that sounds mundane but proved revolutionary: a change of coordinates. In the early 1960s, mathematicians Martin Kruskal and physicist George Sekeres independently developed a new coordinate system that cleanly removed the mathematical singularity at the event horizon. The Kruskal-Sekeres coordinates revealed that the infinity in the original Schwarzschild coordinates was an artifact of the mapping, like the apparent singularity at the North Pole on a flat map of the Earth. The pole is not a special place on the planet, it just looks singular on a Mercator projection. But what the Kruskal-Sekeres diagram revealed about the full structure of Schwarzschild spacetime was genuinely shocking. The complete solution does not describe one exterior region and one black hole interior. It describes four distinct regions of spacetime. Region 1 is the exterior universe we inhabit, the normal spacetime outside the black hole where stars burn and planets orbit. Region 2 is the black hole interior, the region beyond the event horizon where all paths lead toward the singularity. Region 3 is something called a white hole, a time-reversed black hole from which everything escapes and into which nothing can fall. And Region 4 is a second exterior universe, completely separate from our own, connected to Region 1 only through the interior geometry. The Einstein-Rosen bridge connects Regions 1 and 4. On the Kruskal-Sekeres diagram, you can draw a line at a single moment of time that passes from one exterior region through a narrow throat and into the other exterior region. The bridge exists. The connection is real in the mathematical sense. But trace that spatial slice forward in time. Watch what happens. The throat narrows. The connection shrinks. Within an interval so brief that light itself cannot traverse the distance, the bridge pinches shut completely. The two exterior regions disconnect. The passage that existed for a mathematical instant seals itself with the finality of a collapsing tunnel. This is not a slow process that better engineering might outrun. The collapse happens faster than the speed of light, not because anything moves faster than light, but because the geometry itself evolves on a timescale shorter than the light crossing time of the throat. A photon fired into the bridge from Region 1 at the precise moment of maximum width would not reach Region 4. It would hit the singularity instead, arriving at the point of infinite curvature that swallows everything in Region 2. The reason lies in a distinction that is absolutely critical and almost universally misunderstood. The Einstein-Rosen bridge is a space-like surface. In relativity, there are two fundamentally different kinds of connections. A time-like path is one that a physical object, a particle, a spaceship, a beam of light, can actually follow through space-time. A space-like surface is one that stretches across space at a single frozen moment of time. You can draw a space-like surface connecting New York and Tokyo. That does not mean you can teleport between them. You cannot travel along a space-like connection any more than you can travel to last Tuesday. The geometry of space-time does not allow it. The Einstein-Rosen bridge is space-like. It connects two regions across space at an instant, but no physical object can follow that connection because doing so would require moving along a path that the causal structure of space-time forbids. To reach region 4 from region 1, you would first have to cross the event horizon into region 2, and once inside region 2, you are doomed. The singularity lies in your future, not as a place you might avoid by steering cleverly, but as an inevitability encoded in the geometry itself. Inside a black hole, every direction you can travel leads toward the singularity. The bridge to region 4 is not ahead of you. It is behind you in time. It is already gone. This is worth emphasizing because it is the single most important fact about wormholes that popular culture gets wrong. The Einstein-Rosen bridge does not collapse because we lack the technology to prop it open. It does not pinch shut because we have not found the right materials. It is uncrossable because the causal structure of space-time, the fundamental architecture that determines which events can influence which other events, does not permit anything to traverse it. This is not an engineering problem, it is a theorem. In 1965, Roger Penrose proved the singularity theorem that made this precise. Under extremely general conditions, once a trapped surface forms, a region of space-time where light cannot escape, a singularity is inevitable. The collapse of the Einstein-Rosen bridge is not an accident of the Schwarzschild solution's perfect symmetry. It is a consequence of how gravity behaves whenever space-time curves beyond a critical threshold. Penrose won the Nobel Prize in Physics in 2020 for this work, 55 years after the proof. Some physicists hoped that more realistic black holes might tell a different story. Real astrophysical black holes are not perfectly spherical and static. They spin. In 1963, Roy Kerr found the solution to Einstein's equations for a rotating mass. The Kerr geometry is far richer and stranger than Schwarzschild's. The singularity is not a point but a ring. The interior contains additional regions of space-time that, on paper, connect to other universes. Some mathematical paths through the Kerr interior avoid the singularity entirely, threading through the ring and emerging into what appears to be a new space-time. For a brief period, this generated real excitement. Perhaps rotating black holes contained stable bridges. Perhaps the spin provided enough angular momentum to prevent collapse. The excitement did not survive careful analysis. The problem is the inner horizon. The Kerr black hole has two horizons, an outer event horizon and an inner Cauchy horizon. To reach the exotic interior regions, to access the ring singularity and the putative bridge, anything falling in must cross the inner horizon, and the inner horizon is catastrophically unstable. The instability is called mass inflation, identified by Eric Poisson and Werner Israel in 1990. The inner horizon acts as an infinite blue shift surface. Radiation falling into the black hole, even the faintest whisper of a photon, gets compressed and amplified as it approaches this surface. The energy density measured by an observer near the inner horizon diverges, not gradually, explosively. A single photon entering the black hole generates effectively infinite energy at the Cauchy horizon, creating what amounts to a new singularity that seals the passage. This means that the mathematically elegant interior of the Kerr solution, with its ring singularity and its connecting regions, is almost certainly not physically realized. Any real rotating black hole that has ever absorbed even one particle of radiation has had its inner structure destroyed by mass inflation. The pristine Kerr geometry is like a house of cards that collapses the moment a breeze touches it, and in the real universe there is always a breeze. The Reissner-Nordstrom solution, describing a charged non-rotating black hole, tells the same story. It also possesses an inner Cauchy horizon. It also suffers mass inflation instability. It also contains mathematical bridge structures that are physically inaccessible. Every known exact black hole solution in general relativity produces some form of geometric connection between distinct spacetime regions. And in every case, the The physical dynamics destroy that connection before it can be used. The Schwarzschild bridge collapses too quickly. The Kerr interior is destabilized by mass inflation. The Reissner-Nordstrom solution suffers the same fate. The equations build connections. The dynamics tear them apart before anything can cross. This leads to a crucial distinction that runs through the entire story of wormholes: the difference between topology and geometry. Topology describes the large-scale connectivity of a space. It answers questions about how regions are connected, whether holes exist, whether surfaces are bounded or infinite. A sphere and a cube are topologically identical because one can be continuously deformed into the other without tearing. A donut and a coffee mug are topologically identical because each has exactly one hole. To change the topology of a space, you must tear or glue, operations that are discontinuous and violent. Geometry, by contrast, describes the local shape of a space. The distances between points, the curvature at each location, the angles between intersecting paths. Two spaces can have identical topology, but wildly different geometry. A wormhole is fundamentally a topological feature. It is a handle or tunnel in the topology of spacetime, connecting two otherwise distant regions. Topological features are robust. You cannot remove a hole from a donut by stretching or squashing. The connectivity persists through continuous deformations. In this sense, wormhole topology is sturdy. But topology alone does not determine whether anything can physically cross the connection. That depends on the geometry, the specific curvature, distances, and causal structure at every point along the bridge. And in every known physically realistic solution, the geometry conspires to prevent traversal. The throat closes, the curvature becomes singular. The causal structure diverts all paths toward destruction. The topology says connected, the geometry says sealed. Einstein himself was never troubled by any of this. He did not propose the Einstein-Rosen bridge as a mechanism for travel. The 1935 paper was an exercise in mathematical physics, an attempt to model particles as geometric structures in spacetime. The notion that someone might try to send a spacecraft through the bridge would have struck him as irrelevant to his purpose, but the concept escaped the bounds Einstein set for it. In 1957, John Wheeler and Charles Misner explored an idea called spacetime foam. At the Planck scale, the smallest meaningful scale in physics, approximately 10 to the negative 35 meters, quantum fluctuations might cause the topology of spacetime to fluctuate continuously. Tiny wormholes, far smaller than a proton, would form and dissolve in times shorter than 10 to the negative 43 seconds, the Planck time. These microscopic connections would not be passages. They would be quantum froth, the turbulent texture of spacetime at its most fundamental level. Wheeler envisioned these Planck-scale wormholes as part of the basic fabric of reality. At scales we can observe, spacetime appears smooth and continuous. But zoom in far enough, past atoms, past nuclei, past quarks, down to the Planck length, and the smooth fabric might dissolve into a seething foam of transient topological connections. Wormholes everywhere, but each one 100 billion times smaller than a proton, each lasting for a duration shorter than any physical process we can measure. This idea remains entirely hypothetical. No experiment has probed spacetime at the Planck scale, and none is likely to for the foreseeable future. The energy required to resolve structures at the Planck length exceeds anything achievable by particle accelerators by roughly 15 orders of magnitude. But the concept established a principle that matters enormously for our story. Even if wormholes exist at some fundamental level, their natural state is to be submicroscopic, transient, and utterly useless for transport or communication of any kind. So here is where the landscape stands after the first century of wormhole physics. The simplest exact solutions to Einstein's equations produce geometric bridges between distant regions of spacetime. The Schwarzschild bridge collapses faster than light can cross it. The Kerr and Reissner-Nordstrom interiors are destroyed by the mass inflation instability the moment any radiation enters the black hole. Planck-scale wormholes, if they exist at all, are too small and too brief to interact with. Every natural wormhole that general relativity predicts is born dead, sealed shut by the dynamics of the very equations that create it. But the equations do more than just produce dead bridges. They also specify with mathematical precision exactly what it would take to keep a bridge open. If you could somehow intervene in the geometry, if you could introduce the right kind of matter at the right location with the right properties, you might prevent the collapse. You might hold the throat open long enough for something to cross. In 1988, two physicists at the California Institute of Technology asked exactly this question. Michael Morris and Kip Thorne approached the problem backward. Instead of starting with known physics and seeing what geometry emerged, they started with the desired geometry, a stable, traversable wormhole, and asked what physical conditions would be necessary to produce it. The answer they found did not open a door. It revealed a wall built from the deepest principles of energy, stability, and causality that physics has ever uncovered. The nature of that wall and the multiple reinforcing layers that make it impenetrable is where this story goes next. What Morris and Thorne discovered was not merely that wormholes are hard to build. They discovered that the universe actively prevents them from functioning, through mechanisms so fundamental they may define the very structure of physical law. Michael Morris and Kip Thorne did not set out to kill the wormhole dream. They set out to take it seriously. In 1988, working at the California Institute of Technology, they asked the most honest question anyone had ever posed about traversable wormholes. Not whether they sounded cool, not whether they appeared in the equations, but what specific physical conditions would be required, down to the precise mathematical constraints on matter and energy, to hold a wormhole throat open long enough for something to pass through. The question had an unusual origin. Carl Sagan was writing his novel Contact and needed a scientifically defensible method for his character to travel across the galaxy. He contacted Thorne, his colleague at Caltech, and asked whether physics permitted any plausible mechanism. Thorne took the question home, discussed it with Morris, and they began working the problem in reverse. Instead of starting from known matter and deriving what geometry it produced, they started from the desired geometry, a stable spherical throat connecting two distant regions of spacetime, and worked backward to determine what matter would be needed to sustain it. The method was ingenious. General relativity connects geometry on one side of Einstein's field equations to the distribution of matter and energy on the other. Specify the geometry you want, and the equations tell you what energy distribution is required to produce it. Morris and Thorne specified a traversable wormhole. The equations told them what kind of matter must thread the throat. The answer was a death sentence for every wormhole fantasy ever conceived. The matter threading the throat of a traversable wormhole must violate the null energy condition. This is one of several energy conditions in general relativity, mathematical constraints that physicists place on the behavior of matter to ensure that solutions to Einstein's equations behave in physically reasonable ways. The energy conditions are not laws derived from deeper principles. They are assumptions extrapolated from the observed behavior of every form of matter and energy we have ever encountered. And the null energy condition is among the most fundamental. To understand what it says, imagine a beam of light passing through a region of space containing matter. The null energy condition states that as measured by observers traveling along that light beam, the energy density of the matter must be zero or positive. It cannot be negative. This sounds technical, but the consequences are visceral. The null energy condition ensures that gravity is attractive. It ensures that light converges when it passes near matter rather than diverging. It ensures that matter pulls things together rather than pushing them apart. Virtually every substance humans have ever encountered, every element on the periodic table, every gas in the atmosphere, every form of radiation from radio waves to gamma rays, satisfies this condition comfortably. Morris and Thorne showed that at the throat of a traversable wormhole, this condition must be violated. The geometry of a stable throat requires matter that, as measured by light-speed observers, has negative energy density, not merely zero energy, not merely low energy, energy that is less than nothing, energy that falls below the vacuum, below emptiness, below the baseline of empty space itself. Physicists call this exotic matter. The name is generous. Exotic implies rare and unusual. The reality is more extreme. Exotic matter in this context means matter with properties that no known substance possesses, properties that appear to be forbidden by the fundamental structure of quantum field theory in flat spacetime. This is not antimatter. Antimatter has positive energy. A positron, the antiparticle of the electron, has exactly the same mass, and therefore the same positive energy as an electron. When matter and antimatter annihilate, they release energy. That is the opposite of what wormhole throats require. This is not dark energy either. Dark energy operates on cosmological scales, producing a gentle repulsive effect distributed uniformly across the expanding universe. It does not concentrate into the dense configurations that a wormhole throat demands. Dark energy is dilute. Wormhole stabilization requires concentrated negative energy in a compact region. Does negative energy density exist anywhere in nature? The question leads to one of the most fascinating and ultimately frustrating chapters in modern physics. In 1948, the Dutch physicist Hendrik Casimir predicted something remarkable. He showed that quantum field theory requires the vacuum between two uncharged, perfectly conducting parallel plates to have fewer quantum fluctuation modes than the vacuum outside the plates. The restricted space between the plates suppresses certain wavelengths of vacuum fluctuations, like a narrow hallway that cannot accommodate long sound waves. The result is an imbalance. The unrestricted vacuum outside the plates pushes inward. The restricted vacuum between them pushes outward less strongly. The plates experience a net attractive force, drawing them together. More importantly for our story, the energy density between the plates drops below that of the normal vacuum. The restricted fluctuations mean less energy per unit volume in the gap than in empty space. This is, in a very precise sense, negative energy density. Energy below the vacuum level. The Casimir effect was experimentally confirmed in 1997 by Steve Lamoro, who measured the attractive force between a gold-coated sphere and a flat plate separated by distances ranging from half a micrometer to several micrometers. The force matched Casimir's prediction to within 5%. The negative energy density is real, but the enthusiasm ends there. The magnitude of the Casimir energy is extraordinarily small. For plates separated by 1 micrometer, the energy density between them is approximately 10 to the negative 15 joules per cubic meter. To stabilize a wormhole throat, even 1 meter wide, would require concentrations of negative energy that exceed what the Casimir effect produces by dozens of orders of magnitude. The deficit is not a factor of 10 or 100. It is a factor of 10 raised to a power so large that the number itself becomes meaningless in practical terms. Comparing the Casimir energy to wormhole requirements is like comparing the static electricity on a wool sweater to the energy output of a supernova. And the problem goes deeper than mere quantity. Quantum field theory appears to impose fundamental restrictions on how negative energy can accumulate. In the 1990s, Larry Ford at Tufts University and Thomas Roman at Central Connecticut State University developed a series of results known as quantum inequalities. These inequalities place rigorous bounds on the magnitude and duration of negative energy density that quantum fields can produce. The restrictions follow a pattern that Ford and Roman described with a banking metaphor. You can borrow negative energy from the quantum vacuum, but you must pay it back quickly and you must pay interest. The larger the negative energy pulse, the shorter it can last. The longer it persists, the weaker it must be. Ford and Roman showed that for any quantum field satisfying reasonable physical conditions, a pulse of negative energy of magnitude delta E can last for a time no longer than roughly 1 divided by delta E in natural units. This means that a large burst of negative energy is permitted only for an extraordinarily brief interval, far too brief to stabilize a macroscopic wormhole throat for any useful duration. The universe does not forbid negative energy outright. It forbids the sustained accumulation of negative energy that wormholes demand. The averaged null energy condition captures this restriction in a more formal way. While the null energy condition can be violated at individual points, as the Casimir effect demonstrates, the averaged version integrates the energy density along an entire null geodesic, the complete path of a light ray from the distant past to the distant future. This integral, the averaged null energy condition states, must be non-negative. Point violations are tolerated. Accumulated violations along an entire light path are not. Building a traversable wormhole requires sustained negative energy density throughout the throat region. Any light ray passing through the throat must encounter enough negative energy to defocus, to bend outward rather than inward. The averaged null energy condition forbids exactly this. Even if individual points within the throat have negative energy, the total along any complete light path must average out to 0 or above. The universe grants temporary loans of negative energy. It does not grant mortgages. Some physicists have explored whether quantum effects in curved spacetime might produce stronger violations. The Hawking effect, predicted by Stephen Hawking in 1974, involves negative energy flux falling into a black hole as positive energy escapes as thermal radiation. This is a genuine violation of the null energy condition in curved spacetime, but the quantities involved are astonishingly tiny. A black hole with the mass of our Sun has a Hawking temperature of approximately 60 billionths of a Kelvin, producing energy fluxes so feeble they are unmeasurable by any instrument that exists or is likely to exist. Other proposals have invoked the conformal anomaly, a quantum effect in curved spacetime where the expectation value of the stress-energy tensor can violate classical energy conditions. In certain spacetime backgrounds, the quantum vacuum state can produce negative energy densities near horizons or in regions of high curvature, but these effects are always tightly constrained by the average conditions, and they produce quantities that fall short of wormhole requirements by the same staggering margins. The exotic matter barrier alone is sufficient to consign traversable wormholes to the realm of mathematical fiction, but the universe does not rely on a single defense. It backs up the energy condition with two additional barriers, each independently fatal. The first is instability. Even if exotic matter existed in sufficient quantities, a traversable wormhole would be dynamically unstable. It would not sit calmly waiting for travelers. It would vibrate, oscillate, and amplify perturbations in ways that lead rapidly to collapse or runaway expansion. In the early 2000s, several groups of physicists investigated the stability of Morris-Thorne-type wormholes under small perturbations. The results were discouraging across the board. For many classes of exotic matter distributions, the wormhole throat is linearly unstable. A small compression causes it to collapse toward a singularity. A small expansion causes it to blow open, dispersing the exotic matter and destroying the throat structure. The wormhole sits at an unstable equilibrium, balanced on a knife edge between implosion and explosion. The instability is not a quirk of particular models. It reflects a general feature of self-gravitating systems sustained by exotic matter. Ordinary gravitationally bound systems, like stars, achieve stability through a balance between inward gravitational pull and outward pressure. If the star compresses slightly, pressure increases and pushes back. If it expands slightly, pressure decreases and gravity pulls back. This negative feedback creates stability, but exotic matter generates repulsive gravity. A wormhole throat sustained by exotic matter faces positive feedback. Compression reduces the throat radius, which alters the exotic matter distribution, which reduces the repulsive effect, which causes further compression. The system does not restore itself, it accelerates toward failure. Some researchers have proposed stabilization mechanisms involving specific combinations of exotic and normal matter, or modified theories of gravity that change the dynamics. These proposals exist in the theoretical literature, but they require increasingly fine-tuned conditions and increasingly speculative physics. Each proposed fix introduces new complications. Each stabilization mechanism depends on assumptions that push further from established science. The second backup barrier is more absolute than instability, and it strikes at the logical foundations of physics itself. It concerns causality. If a traversable wormhole connects two regions of spacetime that are separated by a distance greater than what light can cross in the available time, then the wormhole functions as a faster-than-light communication channel. Information entering one mouth exits the other at a location that normal signals cannot reach within the same time interval. This is not merely fast, it is causally unprecedented. In special relativity, faster-than-light communication is not just impractical, it is logically equivalent to backward-in-time communication when viewed from certain reference frames. This is a theorem, not a speculation. If observer A can send a message to observer B faster than light, then there exists a reference frame in which observer B receives the message before observer A sends it. The proof follows directly from the Lorentz transformations, the mathematical framework underlying all of special relativity. A traversable wormhole therefore threatens to create closed time-like curves, paths through spacetime that loop back to their own past. An object travelling along such a curve could meet its earlier self, creating paradoxes that challenge the logical consistency of physics. The construction of a time machine from a traversable wormhole is disturbingly straightforward. Follow the logic step by step and feel the ground shift beneath your assumptions about how reality works. Begin with a traversable wormhole, two mouths connected by a short throat. Call them mouth A and mouth B. Place mouth A on Earth. Place mouth B on a spacecraft. At this moment, both mouths experience time at the same rate. Clocks beside mouth A and clocks beside mouth B tick in synchrony. The throat connecting them is short, perhaps only a few meters, even though the two mouths sit far apart in normal space. Now accelerate the spacecraft, carrying mouth B to a significant fraction of the speed of light. Special relativity dictates that time passes more slowly for objects moving at high velocity, relative to a stationary observer. This is not theoretical speculation, it is confirmed fact, measured with atomic clocks on aircraft and satellites, verified to extraordinary precision by the Global Positioning System, which must correct for relativistic time dilation every second of every day. Clocks on the spacecraft tick slower than clocks on Earth. Fly the spacecraft on a long journey, perhaps a round trip lasting 10 years as measured by clocks on Earth. Due to time dilation, the clocks aboard the spacecraft might register only 1 year of elapsed time. When the spacecraft returns and parks mouth B next to mouth A, the two mouths sit side by side in the same location, but they are no longer synchronized. Mouth A has aged 10 years. Mouth B has aged 1 year. The throat connecting them still bridges the two mouths directly, but it now bridges two different moments in time. Step through mouth B and you exit mouth A. Not in the present, but 9 years in the past, because mouth A's clock is 9 years ahead of mouth B's clock, and the throat connects the mouths at their own local times. The paradox materializes immediately. Enter mouth B on Earth in the year 2035, exit mouth A on Earth in the year 2026. Walk across the room. Mouth B is right there, 9 years younger. Wait. Enter mouth B again, exit mouth A in 2017. The loop has no natural stopping point. Each traversal carries you further into the past, limited only by the moment the time offset was first created. Now the true horror emerges. After exiting mouth A in 2026, you could walk over to your younger self, the version of you that has not yet entered the wormhole, and hand them a note. That note did not exist before you entered the wormhole. Where did the information come from? You wrote it after travelling to the past, but you travelled to the past because the wormhole existed, and the wormhole existed because physicists built it. But what if the note contains instructions for building the wormhole? Then the information has no origin. It exists in a causal loop, an effect that is its own cause, a bootstrap paradox that violates every principle of physical causation. This is not a quirk of one particular scenario. It is a generic feature of any traversable wormhole that creates a time offset between its mouths. And creating a time offset requires nothing exotic. Ordinary relative motion or ordinary gravitational fields produce time dilation. Any wormhole whose mouths experience different environments for any duration develops a time offset. The time machine is not an unusual application of a traversable wormhole. It is an inevitable consequence. Stephen Hawking recognized this threat clearly. In 1992, he proposed the chronology protection conjecture. The laws of physics do not permit the creation of closed time-like curves. The conjecture was not proven from first principles. Hawking framed it as a necessary condition for the consistency of physics, and then demonstrated that semi-classical gravity, the framework that combines general relativity with quantum field theory, provides enforcement mechanisms. The mechanism works through quantum vacuum fluctuations. As a space-time geometry approaches the formation of a chronology horizon, the boundary between the region where time travel is possible and the region where it is not, the quantum vacuum becomes increasingly disturbed. Virtual particles circulating along the nearly closed time-like curves amplify their energy with each circuit. The energy density near the chronology horizon diverges, growing without bound as the geometry approaches the critical configuration. This divergent energy produces a gravitational back reaction. The accumulated stress energy alters the space-time geometry, either destroying the wormhole or warping the space-time in a way that prevents the closed curves from forming. The universe does not merely forbid time machines, it actively dismantles them during construction. The closer you get to creating a closed time-like curve, the more violent the quantum vacuum response becomes, until the structure responsible is obliterated. Hawking acknowledged that a complete proof of chronology protection would require a full theory of quantum gravity, which we do not yet possess. The semi-classical calculation breaks down precisely at the point where the energy divergence becomes extreme, indicating that quantum gravitational effects become important. But every calculation that can be performed within the semi-classical regime points in the same direction. The universe resists closed time-like curves with mechanisms that become stronger as the threat becomes more imminent. No known counterexample to the chronology protection conjecture exists within physically reasonable spacetimes. Every proposed time machine configuration that has been analysed in detail has been shown to fail, either through energy condition violations, instability, or the chronology protection mechanism. The conjecture may not be proven, but the evidence is overwhelming. The connection between wormholes and causality violation deserves emphasis because it is often overlooked in popular treatments. This is not a secondary concern. It is the central issue. Every traversable wormhole connecting space-like separated regions is a potential faster-than-light channel. Every faster-than-light channel is a potential time machine. Every potential time machine triggers chronology protection. The chain of logic is airtight within the framework of known physics. 2029. This means that even if exotic matter existed, even if stability could be achieved, the wormhole would still face destruction the moment it threatened to enable causality violation. And since any wormhole connecting distant regions inherently enables faster-than-light signaling, the threat is present from the moment of creation. Chronology protection does not wait for someone to try building a time machine. It activates whenever the space-time geometry approaches a configuration that could, in principle, allow one. There is one additional constraint that operates at the classical level and deserves attention. In 1993, John Friedman, Christian Schleich, and Donald Witt proved the topological censorship theorem. The theorem states that in any globally hyperbolic, asymptotically flat spacetime satisfying the average null energy condition, every causal curve connecting past null infinity to future null infinity can be continuously deformed to a topologically trivial curve. The curve does not need to pass through a wormhole. It can always be pulled back to a simple path that stays in the trivially connected region. The physical meaning is devastating. If the average null energy condition holds, no observer can detect the topology of spacetime through any causal experiment. You cannot send a signal through a wormhole and have it arrive at a distant location in a way that differs from what you could achieve through normal spacetime. The shortcut exists in the topology. The causal structure hides it completely. The wormhole is there, in the mathematical sense, but the universe renders it invisible and unusable to any physical probe that respects causality. Topological censorship is not a conjecture. It is a proven theorem, following rigorously from the average null energy condition and the global structure of spacetime. Its conclusion is unambiguous. In well-behaved spacetimes satisfying physically reasonable energy conditions, wormholes cannot function as shortcuts. The topology connects, the physics conceals. These three barriers, exotic matter requirements, chronology protection, and topological censorship, form an interlocking defense that operates at different levels of physical theory. The exotic matter barrier arises from the relationship between geometry and energy in general relativity. The chronology protection mechanism arises from quantum field theory in curved spacetime. The topological censorship theorem arises from the causal structure of asymptotically flat spacetimes satisfying averaged energy conditions. They are not independent obstacles waiting to be solved one at a time. They are coupled aspects of a single deep constraint. Proposals that attempt to circumvent one barrier typically run afoul of another. Configurations that reduce exotic matter requirements tend to increase instability. Solutions that avoid chronology issues tend to satisfy energy conditions so well that topological censorship applies. The constraints reinforce one another, forming a closed system of prohibitions that has, so far, proven impossible to breach. The Alcubierre warp drive metric, proposed by Miguel Alcubierre in 1994, illustrates this coupling vividly. The Alcubierre solution describes a bubble of distorted spacetime that could, mathematically, transport an object faster than light by contracting space ahead and expanding space behind. It shares the wormhole's central pathology. It requires exotic matter violating the null energy condition, distributed in a precise shell around the warp bubble. It faces the same chronology protection threats, since faster-than-light travel permits closed time-like curves in certain reference frames. And it encounters additional difficulties, including the fact that the interior of the bubble is causally disconnected from the bubble wall, meaning no occupant could steer, stop, or initiate the drive from inside. The Alcubierre metric is not a solution to the wormhole problem. It is a different manifestation of the same set of impossibilities, confirming that the barriers are not specific to wormholes but general features of any spacetime configuration that attempts to circumvent the lightspeed constraint. The Morris-Thorne wormhole was never a blueprint for construction. It was a thought experiment designed to probe the limits of physics, and it succeeded spectacularly at that task. By specifying exactly what conditions a traversable wormhole would require, Morris and Thorne gave physicists precise targets to investigate. The investigation revealed that those targets lie behind some of the most formidable barriers in all of physics. The wall surrounding traversable wormholes is not made of unknown materials or unsolved equations. It is made of energy conditions derived from quantum field theory, stability constraints derived from gravitational dynamics, causality requirements derived from the logical structure of spacetime, and censorship theorems derived from the geometry of well-behaved universes. These are not gaps in knowledge waiting to be filled. They are established results from the deepest levels of physical theory. Yet the story does not end with prohibition. Despite these absolute-sounding barriers, recent decades have seen a burst of experimental and theoretical activity that has brought physics closer to wormhole-like phenomena than ever before. Quantum processors have simulated wormhole dynamics. Analog gravity systems have reproduced wormhole geometry using sound waves and light. Theoretical frameworks have constructed traversable wormholes within specific mathematical contexts. Each of these achievements generated headlines proclaiming breakthroughs. Each requires careful examination to understand what was actually accomplished and what it means. The answer, as always with wormholes, is not what the headlines suggest. What scientists found is not a path toward building real wormholes. What they found is something far more revealing about the nature of space-time, quantum information, and the deep structure connecting them. Every apparent advance toward a wormhole turned out to reveal not a gateway, but a mirror. reflecting back a deeper understanding of why the universe is built the way it is. On November 30th, 2022, the scientific journal Nature published a paper that detonated across the global media landscape like few physics results in recent memory. The headline from the journal's own news team read, "Physicists create a wormhole using a quantum computer." Within hours, the story appeared on every major news outlet on the planet. Television anchors described the dawn of teleportation. Social media exploded with proclamations that scientists had punched a hole through the fabric of space. Comment sections overflowed with questions about when the public could start traveling to distant stars. Almost none of it was true. The experiment was real. The physics was genuine. The result was meaningful. But the interpretation broadcast to the world bore almost no relationship to what actually happened inside the laboratory at the California Institute of Technology. Understanding what the team led by Maria Spiropoulou actually achieved, and why it matters for reasons completely different from those the headlines implied, requires diving into one of the most subtle and frequently misunderstood intersections in all of modern physics, the boundary where quantum information meets gravitational geometry. The experiment used Google's Sycamore quantum processor, the same chip that in 2019 had demonstrated quantum computational advantage by performing a specific calculation faster than any classical supercomputer. For the wormhole experiment, the team used only 9 of Sycamore's 53 superconducting qubits. These 9 qubits were programmed to simulate a heavily simplified version of a quantum mechanical system called the Sakdev-Yeh-Kitaev model. To understand what this experiment actually involved, picture the physical hardware. The Sycamore processor is a flat chip, roughly 25 millimeters on each side, fabricated from silicon and patterned with superconducting aluminum circuits. Each qubit is a tiny resonant circuit, a loop of superconducting metal interrupted by a Josephson junction, a nanoscale sandwich of aluminum and aluminum oxide that allows quantum tunneling of electron pairs. When cooled to operating temperature, each circuit can exist in a superposition of quantum states, encoding information not as a definite 0 or 1, but as a probabilistic blend of both simultaneously. The chip cannot function at room temperature. Thermal noise would overwhelm the delicate quantum states within nanoseconds. To suppress this noise, the Sycamore processor sits inside a dilution refrigerator, a cylindrical apparatus roughly 2 meters tall, constructed from nested metal stages connected by slender tubes. The refrigerator uses a mixture of helium-3 and helium-4 isotopes to reach temperatures of approximately 15 millikelvins, 15 thousandths of a degree above absolute zero. This is roughly 100 times colder than the cosmic microwave background radiation that fills interstellar space. It is among the coldest environments that exist anywhere in the known universe, and it is maintained not by some exotic technology, but by careful plumbing, vacuum engineering, and thermodynamic patience. Control signals reach the qubits through coaxial cables running from room temperature electronics down through the refrigerator stages. Each stage progressively colder, each cable carefully attenuated to prevent thermal photons from reaching the chip. The operations performed on the qubits are microwave pulses, carefully shaped electromagnetic signals lasting between 10 and 100 nanoseconds each. These pulses rotate quantum states, entangle pairs of qubits, and implement the mathematical operations that define the computation. The output of the experiment is not a glowing portal or a ripple in space. It is a string of measurement results, zeros and ones, recorded by classical electronics at room temperature after the quantum computation is complete. Thousands of repetitions are performed to build up statistics. The data is then compared to theoretical predictions derived from the SYK model and its gravitational dual. This is the apparatus that generated headlines about creating a wormhole. A silicon chip smaller than a postage stamp, cooled to near absolute zero inside a metal cylinder, manipulated by microwave pulses through copper cables, producing statistical patterns in a stream of binary digits. The gap between this physical reality and the public interpretation of a portal through space is not a matter of degree. It is a difference in kind, a confusion between a computation about a theoretical model and the physical phenomenon that model describes. The SYK model is not a model of spacetime. It is a model of quantum particles. Specifically, it describes a collection of fermions, particles like electrons, interacting with one another through random couplings. Every fermion interacts with every other fermion, and the strength of each interaction is drawn randomly from a probability distribution. The model was developed independently by Subir Sachdev and Jinwoo Ye in 1993, and by Alexei Kitaev in 2015, and it has become one of the most studied systems in theoretical physics for a reason that has nothing to do with building wormholes. The SYK model is solvable. In the limit of a large number of fermions, the model can be analysed exactly using mathematical techniques from quantum field theory, and when physicists solved it, they discovered something unexpected. The low-energy dynamics of the SYK model, its behaviour at temperatures close to absolute zero, are mathematically identical to the dynamics of a particular theory of gravity in two spacetime dimensions. This gravitational theory, called Jakob-Teitelbaum gravity, describes a simplified universe with one dimension of space and one of time, where a dilaton field controls the geometry. The connection is not metaphorical. It is a precise mathematical correspondence. Every calculation you perform in the SYK model at low energies produces the same numerical answer as the corresponding calculation in Jakob-Teitelbaum gravity. The quantum system and the gravitational theory are dual descriptions of the same underlying physics. This duality is a specific example of a broader framework called the ADS-CFT correspondence, which relates quantum systems without gravity to gravitational theories in higher dimensional spacetimes. Within this correspondence, certain patterns of quantum information dynamics in the SYK model map onto gravitational processes in the dual Jakob-Teitelbaum theory, and one of those gravitational processes is the traversal of a wormhole. Here is what traversal means in this context. In Jakob-Teitelbaum gravity, two black holes can be connected by an Einstein-Rosen bridge. Normally, this bridge is non-traversable, just like the Schwarzschild bridge described in Part 1. But in 2016, Ping Gao, Daniel Jafferis, and Aaron Wall showed that if you introduce a specific coupling between the quantum systems associated with the two black holes, a direct interaction between degrees of freedom on the two boundaries, the bridge can become temporarily traversable. A quantum of information falling into one black hole can emerge from the other. The Gao-Jafferis-Wall mechanism works by injecting negative energy into the wormhole throat. But the negative energy does not come from exotic matter sitting in the throat. It comes from the boundary coupling, the direct interaction between the two quantum systems. In the gravitational picture, this coupling creates a brief pulse of negative energy that holds the throat open just long enough for a single quantum of information to pass through. Remove the coupling, and the throat closes immediately. The Sycamore experiment reproduced the quantum side of this correspondence. The 9 qubits were divided into two groups representing the two boundaries of the Jakob-Teitelbaum spacetime. The team prepared a quantum state on one group, applied operations mimicking the SYK time evolution and the Gao-Jafferis-Wall coupling, and measured the output on the other group. They observed that quantum information inserted on one side reappeared on the other side with characteristics consistent with the gravitational prediction for wormhole traversal. The quantum information transfer was real, the dynamics were faithfully simulated. The correspondence to the gravitational dual was confirmed within the precision of the experiment, but no wormhole existed on the chip. The qubit sat on a silicon wafer inside a dilution refrigerator in a laboratory in California. They were separated by distances measured in millimeters. The interactions between them were mediated by microwave pulses traveling through superconducting circuits at velocities far below the speed of light. No spacetime was curved, no topology was altered. No throat of any kind, geometric or otherwise, connected one group of qubits to the other. The qubits interacted through the same electromagnetic forces that govern every other quantum processor on Earth. The wormhole existed only in the mathematical framework that maps SYK dynamics onto Jacques-Teitelbaum gravity. Calling the experiment a wormhole requires accepting the duality as physically real, interpreting the quantum computation as genuinely equivalent to a gravitational process. This is a defensible position within theoretical physics, where dualities are taken seriously as statements about the identity of physical theories. But it is a very different claim from saying that a wormhole was created in a laboratory. The distinction matters because the public understood the headline in the most literal possible sense. People believed that scientists had opened a portal, that matter could be transported, that the era of faster-than-light travel had begun. None of this is even approximately true. The experiment demonstrated that a quantum processor can simulate the dynamics of a toy model that is dual to a simplified gravitational theory, in which wormhole traversal occurs. Every link in that chain involves abstraction, simplification, and mathematical mapping rather than physical construction. Several prominent physicists objected publicly. Scott Aronson, a quantum computing theorist at the University of Texas at Austin, wrote a detailed critique arguing that the 9-qubit system had been simplified so aggressively from the original SYK model that even the mathematical correspondence to gravity was strained. The full SYK model requires a large number of fermions for the gravitational duality to hold precisely. 9 qubits is far from that limit. The team had used machine learning techniques to find a sparse approximation of the SYK Hamiltonian that could fit on 9 qubits while preserving certain gravitational signatures. Whether this radically pruned system genuinely retains the gravitational dual is a matter of active debate. Peter Shor, the mathematician whose quantum factoring algorithm launched the field of quantum computing, pointed out that the quantum dynamics observed in the experiment could be described entirely within standard quantum information theory, with no reference to wormholes, gravity, or spacetime. The wormhole language was an interpretive layer applied after the fact, not a physical necessity demanded by the results. Two descriptions of the same quantum dynamics coexist, one involving wormhole traversal in a dual gravitational theory, and one involving ordinary quantum information transfer between coupled subsystems. The physics does not prefer one description over the other. This does not diminish the experiment's scientific value. The Sycamore result demonstrated that quantum processors can simulate dynamics relevant to quantum gravity, at least in toy models. It confirmed that the mathematical structures connecting quantum information to gravitational geometry are robust enough to survive implementation on noisy, imperfect hardware. It advanced the quantum simulation program, which aims to use quantum computers to explore problems in quantum gravity that cannot be solved with pencil and paper. But it did not create a wormhole. It did not move physics closer to creating one, and every description that implied otherwise confused a computational simulation with a physical phenomenon, like claiming that a weather simulation on a laptop produces actual rain. The Sycamore experiment belongs to a broader tradition of analog gravity, a research program that constructs laboratory systems reproducing specific mathematical features of curved spacetime. The program has a history stretching back over 4 decades, and it has produced results that are genuinely illuminating about the relationship between mathematics and physical reality. In 1981, William Unruh at the University of British Columbia published a paper that founded the field. Unruh showed that sound waves propagating through a moving fluid obey equations mathematically identical to those governing quantum fields in curved spacetime. If the fluid accelerates past the local speed of sound, it creates a sonic horizon, a boundary beyond which sound waves traveling against the flow cannot escape upstream. Downstream of this horizon, sound is trapped, dragged along by the supersonic flow no matter how loudly it screams. The sonic horizon mimics the event horizon of a black hole with remarkable fidelity. The mathematical structure is the same. The causal structure is the same. Sound inside the sonic horizon cannot reach the outside, just as light inside a gravitational event horizon cannot reach external observers. Unruh showed that if the quantum field theory calculations Hawking had performed for gravitational black holes were repeated for this acoustic system, The sonic horizon should emit thermal phonons, quantized sound vibrations, at a temperature determined by the gradient of the flow velocity at the horizon. Sonic Hawking radiation. Jeff Steinhauer at the Technion in Israel spent more than a decade turning this prediction into an experiment. Steinhauer's path was unusual in modern physics. He worked largely alone, without the large collaborative teams that characterize most experimental efforts in quantum physics. For over a decade, he refined his apparatus, improved his detection methods, published intermediate results, responded to skeptical colleagues, and pushed forward. Many physicists considered the experiment quixotic. Detecting the acoustic analog of Hawking radiation required creating an exotic state of matter, manipulating it with extraordinary precision, and measuring correlations so subtle that distinguishing signal from noise pushed the limits of available technology. The foundation of his experiment was a Bose-Einstein condensate, a state of matter that exists only at temperatures billionths of a degree above absolute zero. Creating one begins with a cloud of rubidium atoms trapped in a vacuum chamber using intersecting laser beams. The lasers are tuned to frequencies that slow the atoms through a process called laser cooling, exploiting the momentum kick that atoms receive when they absorb and re-emit photons. This first stage brings the atoms down to temperatures of millionths of a degree, cold enough to trap them in a magnetic potential well. The second stage uses evaporative cooling. The magnetic trap is adjusted so that the most energetic atoms, the hottest ones, can escape. The remaining atoms rethermalize at a lower temperature, like a cup of coffee cooling faster when you blow on it to remove the hottest steam. This process continues until the atoms reach temperatures of roughly 100 billionths of a degree above absolute zero. At this temperature, quantum mechanics takes over completely. The individual atoms lose their separate identities and collapse into a single collective quantum state. Trillions of atoms behave as one coherent quantum wave. This is the Bose-Einstein condensate. Within this condensate, sound travels extraordinarily slowly. The speed of sound in a Bose-Einstein condensate can be as low as a few millimeters per second, tens of thousands of times slower than sound in air. This is what makes the acoustic black hole possible. To create a sonic horizon in air, you would need supersonic flow exceeding 340 meters per second, the speed of a rifle bullet. In a Bose-Einstein condensate, you need flow exceeding only a few millimeters per second, achievable by gently pushing the condensate with a laser beam. Steinhauer used a step potential created by a laser to accelerate a region of the condensate past this tiny speed of sound. The boundary where the flow transitions from subsonic to supersonic became the sonic horizon. Phonons, quantized sound vibrations, generated on the supersonic side, could not propagate upstream past this boundary. Just as photons cannot escape a gravitational event horizon, the entire sonic horizon existed across a distance of roughly 10 micrometers, comparable to the diameter of a single red blood cell, contained within a condensate cloud, barely visible to the naked eye sitting inside a vacuum chamber on a laboratory benchtop in Haifa. Working with Bose-Einstein condensates, clouds of rubidium atoms cooled to billionths of a degree above absolute zero, Steinhauer created supersonic flows that produced acoustic horizons. In 2016, he published results in Nature Physics, reporting the observation of correlated pairs of phonons emitted from opposite sides of the sonic horizon, one escaping outward and one falling inward, with statistical properties consistent with the thermal spectrum Hawking had predicted. The achievement was remarkable, but Steinhauer was not observing radiation from a black hole. He was observing phonon pair production in an ultra-cold gas. The mathematical framework was identical. The physical substrate was entirely different. Sound waves in a condensate are not photons in curved spacetime. Phonons are collective excitations of atoms. They propagate through a medium. They have a maximum velocity, the speed of sound, that depends on the density and temperature of the gas. None of these features apply to light in a gravitational field. The analog demonstrates that Hawking's mathematical calculation is correct as mathematics. It does not prove that astrophysical black holes radiate, because the derivation of Hawking radiation depends on assumptions about quantum field theory at the Planck scale, assumptions that the analog system does not test. The condensate agrees with Hawking's equations. Whether the actual universe agrees at the relevant scales remains unknown. Optical analogues have pushed the program further. Researchers have designed metamaterials, artificially structured materials with electromagnetic properties not found in nature, that bend light along paths mathematically equivalent to geodesics in curved spacetimes. Ulf Leonhard and Thomas Philbin at the University of St Andrews showed in 2006 that appropriately designed optical media could simulate the geometry of a wormhole. Light entering one region of the metamaterial follows trajectories that, mathematically, correspond to passage through a curved spacetime throat, emerging from another region as though it had traversed a geometric bridge. The optical wormhole looks impressive. Light genuinely enters one place and exits another, along paths that satisfy the equations of geodesic motion in a wormhole geometry. But the light is travelling through a refractive index gradient engineered into a slab of material on a laboratory bench. The spacetime is flat. The geometry is Euclidean. The wormhole exists entirely in the mathematical mapping between the optical equations and the gravitational equations. No topology has changed. No region of space has been connected to another. The photons do not know they are in a wormhole analog any more than water flowing through a pipe knows it is in a fluid dynamics experiment. Around 2020, researchers explored graphene bilayer systems as another class of analog, graphene, a single atom-thick sheet of carbon arranged in a hexagonal lattice, has the remarkable property that its low-energy electronic excitations obey the Dirac equation, the same equation governing relativistic fermions. By engineering specific potential landscapes in graphene bilayers, the team created configurations where electrons propagated through barriers in ways mathematically analogous to wormhole traversal. Electrons entered one side of the potential structure and emerged on the other with transmission probabilities matching predictions derived from wormhole geometry in 2+1 dimensional gravity. The result was described as wormhole-like transport. The mathematical correspondence was genuine. The electrons followed trajectories predicted by the gravitational equations, but the electrons were moving through a carbon lattice on a substrate in a cleanroom. The curved spacetime was absent. The transport was governed by solid-state physics, by band structure and tunneling, and electrostatic potentials, not by the bending of spacetime. The pattern across all analog systems is consistent and instructive. The mathematical structures of general relativity, the equations governing geodesics, horizons, Hawking radiation, and wormhole geometry are not unique to gravity. They arise in fluid mechanics, optics, condensed matter physics, and quantum information theory. The equations are universal. The physics they describe in each context is specific to the substrate. This universality is one of the most significant discoveries of the analog gravity program, though it is rarely framed this way. The fact that wormhole mathematics appears in systems that have nothing to do with space-time curvature tells us something profound. The equations describe patterns of information flow and causal structure that are more general than gravity. Gravity is one physical system that instantiates these patterns. Flowing fluids are another. Optical media are another. Quantum circuits are another. The mathematics is the deep structure. The physical implementation varies, but this universality cuts both ways. If the mathematics can be instantiated in systems without space-time curvature, then observing the mathematics in a laboratory system tells us nothing about whether the corresponding space-time phenomenon exists. Seeing Hawking-like radiation in a condensate does not prove that black holes radiate. Seeing wormhole-like transport in graphene does not prove that wormholes are traversable. Seeing wormhole-like dynamics in a quantum circuit does not prove that wormholes can be created. The analogy is real as mathematics. It is empty as physics. Separate from analog systems, the ER equals EPR conjecture has generated enormous theoretical activity around the relationship between wormholes and quantum entanglement. Proposed by Juan Maldacena and Leonard Susskind in 2013, the conjecture makes a bold claim. Every pair of entangled quantum particles is connected by a non-traversable Einstein-Rosen bridge. Entanglement is geometry. Quantum correlation is spatial connection. The conjecture has deep roots in the ADS-CFT correspondence. In anti-de Sitter space, two entangled black holes on opposite boundaries are connected in the bulk by an Einstein-Rosen bridge. The entanglement entropy between the boundary systems determines the cross-sectional area of the bridge. More entanglement produces a wider, smoother bridge. Maximum entanglement produces the most connected geometry. Maldacena and Susskind proposed that this relationship extends beyond black holes. Any pair of entangled particles, even individual electrons or photons, might be connected by a Planck-scale Einstein-Rosen bridge. The bridge would be far too small and too quantum mechanical to detect directly, but it would provide a geometric interpretation for the non-local correlations that entanglement creates. The idea is beautiful. It unifies two of the most mysterious features of physics, quantum entanglement and spacetime topology, into a single framework. And within the controlled setting of ADS divided by CFT, the correspondence is mathematically precise. But the bridges in ER equals EPR are explicitly non-traversable. They are Einstein-Rosen bridges of the classical type, the kind whose causal structure forbids any signal from crossing. The conjecture does not claim that entanglement enables communication. It claims that the connection that entanglement creates is geometrically real, but physically uncrossable. The correlation is instantaneous. The communication is impossible. The bridge explains why these two facts coexist rather than contradicting each other. This is frequently misunderstood. Popular accounts of ER equals EPR describe it as though entanglement could be harnessed to create traversable connections, as though the wormhole picture implies that entangled particles can exchange messages instantaneously. The mathematics says the opposite. The bridge that corresponds to entanglement is precisely the bridge that blocks information transfer. Entanglement creates correlations that cannot be used to signal. The Einstein-Rosen bridge connects regions that cannot communicate through the connection. The two descriptions are consistent because they describe the same constraint from different perspectives. The Gao-Jeffreys wall result mentioned earlier showed that traversability can be achieved within ADS-CFT, but only through a mechanism with no analogue in our physical universe. The traversability requires a direct coupling between the two boundary quantum systems, an interaction that transmits information between them through a channel external to the bulk spacetime. In the gravitational picture, this external coupling supplies the negative energy that holds the throat open. Without the coupling, the throat remains sealed. This is a crucial point. The Gao-Jeffreys wall wormhole does not violate any of the barriers described in Part 2. The negative energy is not produced by exotic matter. It is injected by the boundary coupling, which in the quantum description is simply an ordinary interaction between two quantum systems. The traversability exists within a theoretical framework where the rules are different from those governing our universe. Our spacetime has positive cosmological constant and expanding geometry. ADS, CFT describes spacetimes with negative cosmological constant and radically different boundary conditions. Results derived within ADS, CFT, are profound for understanding quantum gravity as a theoretical structure. They do not translate into predictions about the spacetime we inhabit. Every experimental result, every analog system, every theoretical construction that approaches wormhole-like phenomena follows the same trajectory. Initial excitement gives way to careful analysis, which reveals that the achievement is real but the interpretation is constrained. The quantum circuit simulates gravitational dynamics but does not curve spacetime. The sonic horizon emits correlated phonons but does not radiate gravitons. The optical metamaterial bends light along wormhole geodesics but does not alter topology. The graphene bilayer transports electrons through wormhole-like barriers but does not connect distant regions. The Gao-Jeffreys wall construction achieves traversability but only within a theoretical framework inapplicable to our universe. Each result is valuable precisely because of its limitations. The Sycamore experiment confirmed that quantum systems can encode gravitational dynamics, supporting the idea that gravity and quantum information are deeply related. The acoustic Hawking radiation confirmed that the mathematical structure underlying Hawking's prediction is robust and universal. The optical and condensed matter analogues demonstrated that curved spacetime geometry emerges from underlying patterns of wave propagation that are far more general than gravity. The Gauss-Jafferis wall result revealed the precise mechanism by which traversability can be achieved within a controlled theoretical setting, clarifying what traversability requires and why those requirements cannot be met in nature. None of these results brings us closer to traveling through a wormhole. All of them bring us closer to understanding what space-time actually is. This is the recurring theme that every near-miss reinforces. The mathematical structures of wormhole physics are real, universal, and deeply connected to the foundations of quantum mechanics and gravity. But the physical phenomenon they describe in the gravitational context, an actual traversable passage through curved spacetime, does not occur. Every analog faithfully reproduces the equations. None instantiates the phenomenon those equations describe in the gravitational context, and every attempt to close the gap between them reveals not a pathway toward construction, but a new insight into why the gap exists. The analogues are not failed wormholes. They are successful experiments that illuminate the relationship between mathematical structure and physical reality. They show that the equations of curved spacetime arise in many physical contexts, suggesting that something deeper than any particular physical system generates those equations. They show that the information theoretic content of wormhole physics, the patterns of correlation and causal structure, can be isolated from the gravitational context and studied independently. They show that quantum entanglement and space-time geometry are connected by more than analogy, that the same mathematical relationships govern both, even when no gravity is present. These insights are leading physics toward a new understanding of space-time itself, an understanding in which geometry is not fundamental but emergent, in which the fabric of space arises from patterns of quantum information rather than existing as a primary entity. In this emerging picture, wormholes are not failed tunnels. They are clues. They point toward the deeper architecture from which space-time is constructed, an architecture that explains both why wormhole geometry appears so naturally in the equations and why wormhole function is so decisively forbidden by the physics. What that architecture looks like, and what the impossibility of traversable wormholes reveals about the fundamental nature of reality, is the final chapter of this story. The answer is not a portal. It is something far more valuable. It is a map of the deepest structure of the universe, drawn in the language of quantum information, written in the geometry of entanglement, and bounded by limits that turn out to be the most important discoveries of all. Every road that physics has built toward traversable wormholes ends at the same destination, not at a door that remains locked for want of a key, not at a chasm that better engineering might one day bridge, but at a flaw, a hard, structural flaw built into the foundations of physical law, visible only to those who have dug deep enough to reach it. The exotic matter barrier, the chronology protection mechanism, the topological censorship theorem, the instability of every proposed throat geometry, these are not separate walls blocking separate corridors. They are surface expressions of a single underlying constraint, a constraint so fundamental that encountering it may be more important than anything a working wormhole could have offered. To understand what that constraint is, and why it matters more than the fantasy it forbids, we need to abandon the question that launched this entire story. We need to stop asking whether wormholes can work and start asking what their failure is trying to tell us. Because the answer to that second question leads somewhere extraordinary. It leads to the discovery that space-time itself may not be what we thought it was. For most of the 20th century, physicists treated space-time as the stage on which the drama of the universe unfolds. Particles move through space-time. Fields oscillate within space-time. Forces propagate across spacetime. The stage itself was considered fundamental, a four-dimensional manifold, smooth and continuous, obeying the geometric rules laid down by Einstein's general relativity. Matter tells spacetime how to curve. Spacetime tells matter how to move. The relationship is dynamic, but the existence of the stage is not questioned. It is simply there, the arena in which everything happens. Over the past 3 decades, this picture has begun to dissolve, not because of a single revolutionary experiment, but because of a convergence of theoretical results pointing toward a conclusion that many physicists initially resisted. Spacetime may not be fundamental. The fabric of the universe, the stage itself, may be emergent. It may arise from something deeper, something that contains no notion of space or distance or geometry at all, something purely quantum mechanical. The strongest pillar supporting this idea is the ADS CFT correspondence, proposed by Juan Maldacena in 1997. The correspondence establishes a precise mathematical equivalence between two radically different theories. On one side is a gravitational theory living in anti-de Sitter space, a spacetime with negative cosmological constant whose geometry curves uniformly inward. On the other side is a quantum field theory, specifically a conformal field theory, living on the boundary of that spacetime, a lower dimensional surface with no gravity at all. The equivalence is exact. Every physical quantity calculated in the gravitational theory can be translated into a calculation in the boundary quantum theory, and vice versa. The two theories are not approximately similar. They are the same theory expressed in two different languages. The bulk spacetime with its geometry, its curvature, its black holes, and its wormholes is completely encoded in the boundary quantum system, which knows nothing about space, distance, or geometry. The boundary theory contains only quantum states, operators, and entanglement. From these ingredients alone, the entire interior spacetime is reconstructed. This is the holographic principle in its sharpest form. The interior of a spacetime is a hologram projected from quantum information on its boundary. The three-dimensional world inside the bulk, with all its spatial structure, emerges from a two-dimensional quantum system that has no spatial interior of its own. Wormholes occupy a privileged position in this framework, but the role they play is nothing like what science fiction imagined. In the ADS CFT correspondence, an Einstein-Rosen bridge connecting two black holes in the bulk spacetime corresponds to quantum entanglement between two subsystems of the boundary theory. The bridge does not exist as an independent geometric object. It exists because the boundary subsystems are entangled. Increase the entanglement, and the bridge widens. Decrease it, and the bridge narrows. Destroy the entanglement entirely, and the bridge disappears. The geometry of the wormhole is a geometric translation of the quantum information structure on the boundary. This relationship was formalized in 2006 by Shinsei Ryu and Tadashi Takayanagi in what has become one of the most cited results in theoretical physics of the 21st century. The Ryu-Takayanagi formula states that the entanglement entropy of a region on the boundary equals the area of a specific minimal surface in the bulk, divided by 4 times Newton's gravitational constant. Entanglement entropy is a measure of quantum correlation between a region and its complement. The minimal surface is a geometric object, the surface of smallest area that encloses the corresponding bulk region. The formula connects quantum information directly to geometry. The amount of entanglement determines the area of a surface in the bulk. The area of a surface determines the geometry of the bulk. Therefore, entanglement determines geometry. Space-time is woven from quantum correlations. Pause here and absorb the magnitude of that claim. It is arguably the most radical proposal in the history of physics. More disorienting than relativity, more counterintuitive than quantum mechanics, because it challenges the one feature of reality that every other theory takes for granted: space. The distance between your hand and this screen. the gap between the Earth and the Moon, the void separating one galaxy from another. All of it, according to this framework, is not a fundamental property of reality. It is a derived quantity, an emergent phenomenon, a macroscopic approximation arising from the collective behavior of quantum degrees of freedom that possess no spatial character whatsoever. An analogy helps. Consider temperature. When you touch a hot stove, the sensation of heat feels absolutely fundamental, as basic and irreducible as any feature of the physical world. But temperature is not fundamental. It is a statistical property of the collective motion of trillions of molecules. No individual molecule has a temperature. A single water molecule is not hot or cold. Temperature only comes into existence when enormous numbers of molecules interact, and their average kinetic energy produces the macroscopic quantity we experience as warmth. Temperature is real. You can measure it, predict it, and burn yourself on it, but it is not a fundamental ingredient of reality. It emerges from something deeper. The holographic principle suggests that space works the same way. No individual quantum degree of freedom on the boundary theory has a position in space. There is no distance between two boundary qubits, because the boundary theory contains no notion of spatial depth. Distance, separation, geometry, these properties only emerge when enormous numbers of boundary degrees of freedom entangle in specific patterns. The three-dimensional space we move through is the macroscopic consequence of quantum correlations among microscopic constituents that individually know nothing about space. If this is correct, and the mathematical evidence is formidable, then certain questions about space-time dissolve rather than get answered. Asking whether you can take a shortcut through space is like asking whether you can take a shortcut through temperature. The question treats the emergent property as if it were the fundamental substrate. At the level where reality actually operates, there is no space to shortcut through. There are only patterns of quantum entanglement, and those patterns obey rules, the rules of quantum mechanics, that determine what configurations are possible and what configurations are forbidden. A traversable wormhole in this picture is not a physical tunnel blocked by physical barriers. It is a pattern of entanglement that the rules of quantum mechanics do not permit. The impossibility is not mechanical, it is structural. It lives at the level of the underlying quantum system, not at the level of the emergent geometry. The geometry merely reflects the impossibility in spatial language, translating a quantum constraint into the statement that no path connects the two sides of the bridge. If this picture is correct, and the mathematical evidence within ADSEEF is overwhelming, then the impossibility of traversable wormholes acquires a meaning that goes far beyond the frustration of science fiction fans. A traversable wormhole would allow a signal to take a shortcut through the bulk spacetime, traveling between two boundary regions faster than light could travel through the normal geometry. But in the holographic picture, the bulk geometry is determined by the entanglement structure of the boundary theory. A shortcut through the bulk corresponds to a violation of the entanglement structure. It would mean that quantum correlations on the boundary permit information transfer at rates faster than the boundary theory allows. And quantum mechanics does not permit this. The no-signaling theorem, one of the bedrock results of quantum information theory, states that entanglement cannot be used to transmit information faster than light. Two entangled particles share correlations that are instantaneous but cannot be harnessed to send a message. The correlation exists. The communication does not. This is not a technological limitation. It is a mathematical theorem derived from the structure of quantum mechanics itself. The non-traversability of the Einstein-Rosen bridge is the geometric expression of the no-signaling theorem. The bridge connects two regions. Information cannot cross it. Entanglement connects two subsystems. Information cannot be transmitted through it. These are the same constraint, expressed in two different languages. The wormhole does not fail because of insufficient exotic matter or inadequate technology. It fails because the quantum information structure from which space-time emerges does not permit the corresponding shortcut. This realization transforms the meaning of every barrier encountered in parts 1 through 3. The exotic matter requirement is not a materials problem. It is an information-theoretic constraint encoded in geometric language. Holding a wormhole throat open requires negative energy density, which corresponds to a pattern of quantum correlations on the boundary that violates the no-signaling theorem. The correlations cannot exist, so the energy cannot exist, so the throat cannot be held open. The chain of impossibility runs from quantum information theory through holographic duality to semi-classical gravity, connecting the most microscopic laws of physics to the largest scale properties of spacetime. The chronology protection mechanism acquires similar depth. Closed time-like curves in the bulk correspond to causal loops in the boundary theory. Quantum mechanics forbids causal loops because they would allow information to influence its own past, violating the unitarity of quantum evolution. Unitarity, the requirement that quantum probabilities always sum to 1, is the most fundamental consistency condition in quantum mechanics. Any process that violates unitarity produces nonsensical predictions, probabilities greater than 100% or less than 0. The chronology protection mechanism is not Hawking's conjecture imposed from outside. It is the geometric shadow of unitarity, projected from the boundary theory into the bulk spacetime. Topological censorship follows the same pattern. The theorem states that observers in the bulk cannot detect the topology of spacetime through causal experiments. In the holographic picture, this means that the boundary theory, which determines all observable physics, does not encode the topological information in a way that bulk observers can access causally. The topology exists in the mathematical structure, the physics hides it. The boundary theory knows the topology, the bulk observers cannot read it. Each prohibition, viewed through the holographic lens, stops being an arbitrary restriction and becomes a necessary consequence of the quantum information structure underlying spacetime. The universe does not forbid traversable wormholes through a list of unrelated rules. It forbids them through a single principle. Spacetime geometry is emergent from quantum entanglement, and the rules governing entanglement do not permit the geometric shortcuts that traversable wormholes would represent. This principle extends into territory that the wormhole question alone could not have reached. In 2012, 4 physicists, Ahmed Almhiri, Donald Marolf, Joseph Polchinski, and James Sully, published a paper that detonated across theoretical physics with an impact comparable to the original black hole information paradox. Their argument, which became known as the firewall paradox, demonstrated that 3 apparently reasonable assumptions about black hole physics cannot all be simultaneously true. The 3 assumptions were these. First, the event horizon of a sufficiently old black hole is smooth, meaning an observer falling through it notices nothing unusual, as general relativity predicts. Second, quantum evolution is unitary, meaning information is never truly destroyed, even by black holes. Third, effective quantum field theory is valid outside the black hole horizon, meaning the laws of physics we understand apply in the region where we can make measurements. Almhiri, Marolf, Polchinski, and Sully showed that these 3 assumptions lead to a contradiction. If quantum evolution is unitary, then the Hawking radiation emitted by the black hole must be entangled with the black hole's internal degrees of freedom in a specific way to preserve information. But the same radiation must also be entangled with earlier Hawking quanta that have already escaped, because the outgoing radiation forms a thermal state with specific correlation properties. Monogamy of entanglement, a theorem of quantum mechanics stating that a quantum system maximally entangled with one partner cannot be entangled with another, forbids both entanglement relationships from holding simultaneously. Something must give. Either the horizon is not smooth, and in falling observers encounter a wall of high-energy quanta, a firewall that destroys anything crossing the horizon, or unitarity is violated, meaning information is genuinely lost and quantum mechanics breaks down, or effective field theory fails in a regime where we expected it to hold, meaning our understanding of physics outside black holes is fundamentally incomplete. Each resolution carries devastating implications, and every proposed resolution connects directly to the wormhole story. If the firewall is real, then the interior of the black hole, the very region where the Einstein-Rosen bridge exists, is not a smooth space-time at all. Infalling observers do not cross a horizon into a bridge-connected interior. They are incinerated at the boundary. The wormhole interior does not physically exist as described by the classical geometry. It is an artifact of an approximation that breaks down precisely where it would need to hold for the bridge to function. If unitarity is preserved through a different mechanism, as most physicists believe it must be, then the resolution likely involves a radical revision of how the black hole interior is constructed from boundary data. Several proposals along these lines have emerged. One of the most influential, developed by Maldacena and Susskind, argues that the entanglement between Hawking radiation and the remaining black hole is itself an Einstein-Rosen bridge, connecting the radiation to the interior through a non-traversable wormhole. The interior geometry is rebuilt from the entanglement structure of the radiation. The bridge is not a passage, it is an encoding scheme. The interior of the black hole is a quantum error-correcting code, a way of storing information redundantly so that it can be recovered from the radiation without ever being accessible through the bridge itself. This perspective, connecting wormhole geometry to quantum error correction, represents one of the most remarkable developments in 21st century physics. In 2015, Ahmed Almheri, Shi Dong, and Daniel Harlow showed that the Ryu-Takayanagi formula, connecting entanglement entropy to geometric area, can be understood as a statement about quantum error correction. The bulk spacetime is a code. The boundary theory is the physical system that runs the code. Points in the bulk interior are logical qubits encoded in the entanglement structure of boundary qubits. The geometry of spacetime, including its distances, curvatures, and topological features, describes the structure of the code. In this framework, the non-traversability of wormholes is a feature, not a bug. The Einstein-Rosen bridge is part of the error-correcting structure that protects information in the interior from being accessed by simple operations on the boundary. The bridge exists because information is encoded redundantly across both sides. The bridge is sealed because the encoding is designed to prevent unauthorized access. Traversing the wormhole would be equivalent to decoding the quantum error-correcting code, extracting the logical information from the physical qubits. Quantum error correction theory tells us exactly how hard this is, exponentially hard, requiring operations whose complexity grows exponentially with the entropy of the system. Leonard Susskind formalized this in his quantum complexity conjecture, proposed in 2014. The conjecture states that the volume of the spacetime region behind a black hole horizon, the length of the Einstein-Rosen bridge interior, grows in proportion to the computational complexity of the quantum state describing the black hole. Complexity here is a precise technical concept from computer science. It measures the minimum number of elementary quantum operations needed to prepare a given quantum state from a simple reference state. For a black hole, computational complexity grows linearly with time for an extraordinarily long period. The bridge gets longer every moment. It does not stop growing until the complexity reaches its maximum value, which takes a time exponential in the entropy of the black hole. For a stellar mass black hole, this timescale exceeds 10 to the power of 10 to the 77 years. That number is so large that writing it out in full, using every atom in the observable universe as a digit, would not provide enough characters. Let that timescale settle into your intuition by building it layer by layer, from scales the human mind can still grasp. The universe is approximately 13.8 billion years old. That is the time since the Big Bang, since the first hydrogen atoms formed, since the cosmic microwave background was released, since the first stars ignited in the darkness. All of human history, all of Earth's geological evolution, all of stellar evolution across every galaxy we can observe, fits within 13.8 billion years. Now, stretch forward. The last ordinary stars, the red dwarfs, will exhaust their hydrogen fuel in roughly 100 trillion years. That is thousands of times the current age of the universe. By then, every galaxy will have faded into a collection of dead stellar remnants. white dwarfs cooling toward absolute zero, neutron stars spinning down to silence, and black holes drifting through eternal darkness. Then the black hole era begins. Stellar mass black holes evaporate through Hawking radiation over timescales of approximately 10 to the power of 67 years. Supermassive black holes, the monsters at galactic centers, take longer, perhaps 10 to the power of 100 years. That is a 1 followed by 100 zeros, a number already beyond meaningful comparison to anything in human experience. When the last black hole evaporates, the universe enters its final state, a thin haze of particles and low-energy photons spreading through expanding space forever. The wormhole's complexity recurrence time has not yet begun to register. 10 to the power of 10 to the 77 years exceeds the black hole evaporation era by a margin so extreme that the black hole era itself rounds to zero by comparison. Imagine. The black hole evaporation timescale is 10 to the power of 100 years, a 1 followed by 100 zeros. That number already defies comprehension. The wormhole's complexity recurrence timescale is 10 to the power of 10 to the 77 years. The exponent alone, 10 to the 77, dwarfs the googol by a margin beyond meaningful comparison. This is not merely a bigger number in the same family. It belongs to a different category of largeness entirely, a number so extreme that the entire black hole era, already incomprehensibly long, vanishes to a rounding error beside it. The timescale on which the wormhole's computational lock might spontaneously open through random quantum fluctuations makes the death of the last black hole look like the blink of an eye. No physical process in the universe operates on this timescale. No star, no galaxy, no structure of any kind persists for even an infinitesimal fraction of this duration. The atoms themselves will have long since decayed if proton decay occurs. The universe will have expanded to such a degree that no two particles remain in causal contact. The wormhole remains sealed not for billions of years, not for trillions, not for googols, but for a duration that makes the entire physical history of the cosmos, from Big Bang to heat death, look like a single tick of a clock that has not yet begun to count. This is the lock the universe places on the wormhole interior. Not a physical wall, not a material barrier. A computational encryption so deep that the lifetime of every star that will ever exist amounts to zero on its timescale. The universe does not merely prevent wormhole traversal, it buries the possibility beneath a mountain of time so vast that the concept of waiting becomes meaningless. Traversing the wormhole would require the complexity to decrease, effectively running the quantum computation backward. But generic quantum systems increase in complexity monotonically for exponentially long times. Decreasing complexity requires fine-tuned operations that are effectively impossible without complete knowledge of the quantum state, knowledge that is exponentially hard to obtain. The wormhole is sealed by computational complexity, not by a physical wall, not by a material barrier, but by the sheer impossibility of performing the quantum operations needed to decode the bridge interior in any reasonable time. The universe encrypts the wormhole using the most powerful cipher physics allows, the exponential complexity of quantum many-body systems. This brings us to the deepest insight that the wormhole story delivers. The inability to traverse a wormhole is not a failure of human ingenuity. It is a structural property of spacetime that reveals how reality is constructed. Consider what a functioning wormhole would mean in the holographic framework. It would mean that the quantum error-correcting code protecting the bulk interior could be broken by a physical process. It would mean that information encoded in the entanglement structure of the boundary could be extracted through a shortcut, bypassing the exponential complexity barrier. It would mean that the causal structure of the boundary theory, which determines which measurements can access which information, could be circumvented by a geometric trick in the bulk. Every one of these implications violates established principles of quantum information theory. Quantum error-correcting codes are specifically designed to prevent unauthorized information extraction. The complexity barrier is not a limitation of current algorithms, but a fundamental feature of quantum mechanics. The causal structure of quantum field theory, embodied in the no-signaling theorem, cannot be bypassed by any physical process consistent with unitarity. The impossibility of traversable wormholes is therefore equivalent to the consistency of quantum mechanics. The two statements are not merely related. They are, within the holographic framework, the same statement expressed in different languages. Wormholes cannot be traversed because quantum mechanics is consistent. Quantum mechanics is consistent because the patterns of entanglement from which space-time emerges obey strict structural rules that no physical process can violate. This conclusion reframes the entire 90-year history of wormhole physics. The Einstein-Rosen bridge was not a failed transportation technology. It was the first glimpse of a deeper truth about the relationship between quantum information and geometry. The exotic matter barrier was not an obstacle to be overcome. It was the geometric expression of constraints on quantum energy that ensure the stability of the vacuum. The chronology protection mechanism was not a cosmic sensor imposed from outside. It was the geometric projection of unitarity, the most fundamental consistency requirement of quantum mechanics. The topological censorship theorem was not an arbitrary restriction. It was the mathematical statement that quantum information cannot be accessed through geometric shortcuts. Every barrier was a discovery. Every prohibition was a lesson. The walls surrounding the wormhole are not the boundaries of human knowledge. They are the structure of physical reality, made visible by the attempt to violate it. And this structure has a name, or at least the beginnings of one. Physicists are calling it emergent space-time. The idea that space, time, distance, and geometry are not fundamental ingredients of reality, but emergent properties arising from quantum entanglement among microscopic degrees of freedom that have no spatial character at all. In this picture, asking why wormholes cannot be traversed is like asking why you cannot walk to a colour. The question assumes that the geometric language describing wormholes is fundamental. If geometry is emergent, the question dissolves. Wormholes are features of the emergent description, not the underlying reality. They appear in the geometric language because certain patterns of entanglement have bridge-like topology. They cannot be traversed because the underlying entanglement structure, which is the actual physical reality, does not permit the corresponding information transfer. The closest thing to a real wormhole turned out to be the most important thing physics has found in decades. Not a gateway, not a shortcut, not a portal to another star, but a window into the construction of space-time itself, a demonstration that geometry arises from information, that space emerges from entanglement, that the fabric of the universe is woven from quantum threads too fine for any classical probe to trace. We did not find a passage through space. We found the reason passages cannot exist, and that reason illuminated the deepest architecture of reality more than any shortcut ever could have. The Einstein-Rosen bridge, born from a wartime calculation on the Eastern Front in 1916, passing through 9 decades of theoretical exploration, mathematical proof, laboratory simulation, and philosophical confrontation, has finally delivered its message. Not the message we wanted, not the promise of cosmic travel or instantaneous connection, but something rarer and more lasting. The universe is not a place with hidden doors waiting to be discovered. It is a structure whose deepest rules forbid those doors, and in forbidding them, reveal how reality itself is made. The wormhole that cannot be crossed is not a cosmic disappointment, it is a cosmic declaration. Space-time has an architecture. That architecture protects causality, preserves unitarity, encodes information, and emerges from entanglement. Every failed attempt to traverse a wormhole has added another line to the blueprint of that architecture. The closest thing to a real wormhole taught us not where we could go, but what we are made of. Space, distance, geometry, the very fabric that separates here from there, emerges from quantum information following rules so precise that no shortcut can circumvent them. The bridge is real in the mathematics. It is sealed in the physics. And the reason it is sealed is the most profound discovery the search for wormholes has ever produced. We are not travellers blocked at a gate. We are students reading a message written in the geometry of spacetime itself. A message that says, this is how reality is built. Not with shortcuts, not with tunnels, but with entanglement, information, and the quiet, unbreakable logic of quantum mechanics weaving the fabric of everything that exists.